This is the final unit of this module where we're going to look at some physical techniques in inorganic chemistry. So they are mostly analytical tools that are used to analyze inorganic samples. The types of methods that we will use and have a look at are diffraction methods, absorption spectroscopy, resonance techniques, ionization-based techniques, and chemical analysis. In this part, we're going to deal with diffraction methods. So this is kind of like a graphic of what we see when we see diffraction. This is a diffraction grating with one hole. And what happens when we have more than one hole, we start to see some interference patterns, which you can see on the blue diagram on the right-hand side. What is diffraction? Well, diffraction really is the scattering of radiation with a wavelength of about 1 angstrom from crystals. And essentially it is any interpretation of diffraction patterns is going to provide structural information about the material or the compound that we're looking at. We can often tell the complete molecular and ionic structure from this data, and crystallographers use the angstrom unit as bond lengths typically lie between 1 to 3 angstroms, and X-ray wavelengths lie between 0.5 to 2.5 angstroms. The picture that you see on the right-hand side shows exactly what diffraction is all about. So we have in-phase radiation coming in, and it strikes a plane of atoms and is diffracted off. Okay, and of course there's some calculations involved. We generally use something called the Bragg equation. So what I'm indicating to you here on the bottom of the slide there is called the Bragg equation for diffraction. We can use different sources for diffraction. So the technique of single crystal X-ray diffraction requires a single crystal of the compound, and the single crystal is then analyzed by X radiation. Powder diffraction requires polycrystalline powdered material and is analyzed with X-ray diffraction. Neutron diffraction, the material can be either single crystal or polycrystalline, and the source of the radiation is now a neutron source. It's no longer X-ray sources. We can also use a synchrotron. A synchrotron is a facility that has a particle accelerator that generates high energy radiation so that we can analyze samples. So for powder X-ray diffraction, we have what you see on the slide here. We have a polycrystalline sample that is exposed to X-rays that the diffracted beams then are emitted and collected onto a detector. So at the top right-hand side in this diagram over here, you can see that we have the X-ray tube that is focused on the sample plate, and the polycrystalline material is placed on the sample plate here, and then the diffracted beams hit the detector, and we have a measuring circle that goes 360 degrees around the detector. So what we will see in some instances, if we look at this diagram, we will see what's called powder rings, and what we actually get out on the bottom right hand side over here is the powder pattern, and the powder pattern is essentially a fingerprint for each compound that is analyzed. So this is an example powder X-ray diffraction pattern of a different polymorph of titanium dioxide in paint, and it measures in this axis here the intensity of the diffracted beam versus the angle at which the X-ray source is given, so in that direction. So you will see that at different 2 theta angles, you start to see some peaks emerging, which are characteristic for that material. In this case, it's characteristic for titanium dioxide. On the left, As I've said, shown you on the previous slide, we have the powder diffraction pattern of different polymorphs of titanium dioxide, and on the right we have a powder pattern showing some mixed oxides. So we have rutile and anatase, which are different polymorphs of titanium dioxide. So if you look on the right hand side over here, and then we have magnesium titanate, magnesium oxide, and carbon. And of course the key will show you which peaks belong to which material. This powder pattern was collected at different temperatures. You can see there's varying temperatures on the side here, if I just show you. And you will see that the key tells you which part of the material in the mixed oxides correspond to the different materials. Now, the way that this is obtained is comparing against standards. So that's how one can identify components in samples and mixed oxides. For single crystal X-ray diffraction, only a single crystal is used. So at the top left-hand side over here, this diagram here, this is a schematic showing the X-ray beam hitting the crystal, and then the X-rays that are diffracted from the crystal planes and the atoms within the single crystal are projected onto a moving plate. So in this diagram over here, we have a single crystal that is mounted onto a loop, and the bottom picture on the left here is a schematic of a instrument, and in the yellow circle is the detector. So this is what you will see on the detector. So the diffracted beams come off onto the detector, and then we get a diffraction pattern that looks like the one that you see on the right. It actually looks like a night sky. So you can see bright white dots against a dark reddish background. This is called a single crystal X-ray diffraction pattern, and from this diffraction pattern we can use complex mathematical algorithms to determine the structure. So we can determine the structure of the material. So on the left-hand side, you can see cisplatin, which is a material that is used for treating cancer. And on the right-hand side is an arbitrary organic molecule that we can determine the structure of. So with the diffraction methods, we can use neutron diffraction because this is a very useful tool for the structure determination of light atoms such as hydrogen atoms. Hydrogen atoms don't scatter X-rays very well, but they do scatter neutron radiation very well. Neutron diffraction can also be very useful when two elements have the same scattering power when analyzed by X radiation. So, for example, you might find that iron and copper, which are very close to one another on the periodic table, will scatter X radiation very similarly, and especially since there's only one electron difference between two elements in a periodic table, say, that it becomes tricky to tell them apart. But you can use neutron radiation because the scattering power of these elements is significantly different. So this is the reason why we would sometimes go to neutron diffraction, would be to try to distinguish between whether we have an iron or a copper, for example.